Okay, let's get started. How'd you all make out on, whoa, didn't think that I would do that, but it did it. I guess this really does copy it all. Go back here. Okay. Paste. How'd you all make out on this one? Able to get results? Anybody do it? No, yes? How about in TV land? Anybody do it? Did you forget or didn't want to take it? That's okay. I didn't assign it as a homework, but it's kind of an easy one to do if you look and if you see that maybe I can move one thing over either to the left or the right. And remember, I can pretty much do the moving things. I can either move a summing junction or I can move a pickoff point. From my perspective, moving this pickoff point, come on, why aren't you writing? I have no idea why this pen stopped working. Moving this pickoff point over to here. And again, once you're on that line, you can move it at any point. Moving that pickoff point to the other side of G2 is going to make it so that I just have this feedback path that I can combine. So my suggestion would be, here's my summing junction. Here's G1. Here's a summing junction. Here's G2. I'm going to feed back H2. This is plus to minus. I'm also going to feed back H1. This is plus to minus. And you can see I move this pickoff point to the other side of the equation, and then I run it into a summing junction, right? So let's move that way out over here so we can give ourselves some room. This is plus, and we know yep. How's that? And we can see, or we know that what we have coming in here is this V3 point, which is not the same as V4. The difference between V3 and V4 has been multiplied. I'm sorry, V3 has been multiplied by G2 to get to V4. So this node right here is the V4 node, right? And if I want to move my pickoff point, I want this to be V3. So what do I need to multiply to get that to be V3? Coming in as V4, coming out as V3. Here's my equation. What would you go ahead and multiply V4 by to get to V3? 1 over G2, right? Because V3 equals V4 divided by G2, correct? So now I can continue. And this is G3. This is H3. And that's my output. So now I can start to combine things, right? So I'm going to work on this area over here first, because what I want to do is I want to see how this whole element here is summed together, because this is a plus and a feed forward, but the summing block is part of a feedback path. So maybe what might be a little bit easier is to draw my summer, create G1. Here's my summer. Here is G2. Here is H2. Here is H1. Plus, minus, plus, minus. So I'm going to put a summer over here, and I'm only going to make that a 2 input summer. And the reason why I'm doing that is because I'm going to break this last path off as its own summer. But now I've got it set up in negative feedback, right? Much, much easier to see that when I break out those elements that way. And now we can do things simultaneously, right? We can take this and simplify it, and we can take this and simplify it. So let's go ahead and do that. Here's my summer. Here's G1. What does this become? Once I put it in my summing junction, what is this? Or I put inverted negative feedback loop. It's G over 1 plus GH, right? So it is G2 over 1 plus G2 H2. I still have my H1 summer over here, plus to minus. This over here, now I'm going to combine this as in one step here, so I can combine that one. And what do I have? I have a block. They're added together. What is the gain of just a line? It's 1. 1. And then the gain up above is there. Now I'm over to this feedback path. That becomes G3 over 1 plus G3 H3. So I did 3 sort of combination ones because I was kind of meticulous up front. I broke them up into individual spots, so it was pretty easy to combine them individually, and then I could do that all in one step. Now I've got one more feedback block to take care of. So this block over here, this is going to be a little more work. This is going to be G2 over 1 plus G2 H2 all over, well, don't forget my G1 there, all over 1 plus G2 G1 1 plus G2 H2 times H1, right? Putting these 3 elements in this feedback path, combine those all, gives me this. Now I'm going to do my fractions and fractions approach. So common denominator, what I end up with, and I'm going to do this fairly quickly. If anybody gets stuck, just let me know and we can do the process out. 1 plus G2 H2 plus G2 G1 H1. Right, just by doing common denominator, inverting and multiplying, that's my term. So what I'm left with is G2 G1 over 1 plus G2 H2 plus G2 G1 H1. Sorry about that. Let me make the block a little bit bigger, so I'm not cramming it in here. And then that's in cascade with this. And then that's in cascade with this. Now I just have to multiply all those together. So my final result, G2, G1 over 1 plus G2, H2 plus G2, G1, H1. That's my first block. Multiplied by 1. Actually, let's make it easier. I'm going to put this under a common denominator. Multiply that by And then we can just put that all at one fell swoop. Hopefully what you can see is I can cross out a G2 here. Everybody see how I did that? Just to get rid of that G2 term. So I'm left with G1 times G3 times G2 plus 1 all over to H2 plus G2, G1, H1. And all of that is multiplied by 1 plus G3, H3. That's it. Questions on that? Feel like you all could do that during a test? Not yet, but maybe. That's why I encourage you, right, to practice this over the weekend. For those of you who showed up a couple minutes late, did anybody practice this over the weekend, this problem? Okay, just suggestions, but if you see stuff like this on the test, don't be upset like, whoa, what happened? What happened? Yes, sir. Yeah, this is in the homework. Yeah. And well, we had one and then we have this, I think this other homework's been posted. I'll double check, but I think it's been posted already, right? The new homework that has the block diagram stuff. Okay. But this is the second or third example we've done in class. We had a lot of practice problems, right? But there's lots more. So any questions on how to do these? So here's the process. You can take a look. You can walk through, but there's your final answer. All right. I like to do it kind of step by step because you can see that sometimes when you go from here to here, it's not too bad. Oops, going the wrong way. That's why looking weird. So from here to here, I showed you how I moved that block, but here's the problem is I combined all three of those in sort of one fell swoop. This way I can break it up and make it a little easier to see how that's being done. So you get the idea. But the final answer is check out. All right, how about I give you 5 minutes. Instead of G's and H's, I'm going to give you Laplace variables. And the reason why I'm going to give you Laplace variables is I want to actually see, are you able to come up with an actual expression that has S terms in it and no G's and H's? Because ultimately what we're trying to do, we have these G's and H's, but that makes it so that we can represent a fairly complicated block with just one variable. What we really need to do is get something like this because we're looking again for that denominator in our overall system transfer function. So we want to go ahead and combine that. So I'll give you 5 minutes to give this one a whirl. It'll probably be not the week after break, but the week after break. Couple more minutes. Yes, sir. Go to the transfer function, which transfers the input to the output. C equals R times the transfer function, which the transfer function, it transfers the output to the input, the input to the output. So that multiplied by your input gives you C. So the transfer function is equal to C over R, right? All right, how would you tackle this one? Any thoughts? I would pretty quickly combine that, right? To the feed forward, sum those together. And then because I've got two feedbacks over here, I would create two summing junctions. And I would probably move this one to this side so that I can get this one combined here. Then I get a forward gain path, and then I can wrap it all together. So let's take a look at that in real time. Do you want me to do it by hand on whiteboard, or is this okay to do it this way? What do you think? There's a lot of algebra that gets skipped when we go from this to this. Okay. So copy that over. Paste that here. All right. So these two combined is just S squared, right? When I put the two of them together, that just becomes S squared. So I have G over 1 plus GH, right? So H in this case is equal to 1 over S. So S squared multiplied by 1 over S gives me that term. When I multiply those out, that's S squared over 1 plus S, correct? No common denominator stuff that I need to do here. So now I'm going to break my summing junction up into two separate ones. And I'm going to come in overhead here. This block is S squared over 1 plus S. I'm going to steal from that location. Then I'm going to run 1 over S. multiply that by S. And I've got a simplified network, right? Now I can combine this, which becomes G all over 1 plus GH. H is equal to 1, right? This is unity feedback. So I can do quickly and get those under a common denominator. Anybody not see how I got that term under a common denominator? Simplified it down. I just moved the 1 over S over here, 1 plus S over there, and then inverted and multiplied, and I ended up with that term. So I'm almost done. I've only got one more block to combine. This is S squared over 1 plus S squared. This is 1 over S. Move that up a little bit. This is S. And I've got that value there. I can combine these two, right? And how do I combine them? That becomes 1, and this S squared just becomes S, right? S squared times 1 over S becomes just S. And so when I do the negative feedback, my G, which is S over 1 plus S squared, over 1 plus GH, times S. I put it again under a common denominator, invert and multiply. I have S over 1 plus S squared plus S squared, which is S over 2S squared plus S plus 1. And that's my final transfer function. Yes, sir. Yep.
First, second, so does it?
Way up over here? Or this one right here?
Not the S squared, the next one.
So right here, combining these three.
Yeah.
No, if it's negative feedback, it's G over 1 plus GH. If it's positive feedback, it's G over 1 minus GH.
What if that would be positive because it's two positives going in your sign direction? Combining that? That's not the negative version. That's not what we have, right?
This stuff right here. Is that what you mean? Oh yeah, you're right. So I made a mistake here. This is not H. This is feed forward. My arrow over here is this way. So that is incorrect. Thank you. What I end up with is S squared plus 1 over S, right? So I got to clean this up a little bit. That becomes S squared plus 1 over S. Not multiply. So what's that? The feedback, we're going to do that feedback right here. So this feedback, this is a feedback path, right? So now it's going to be G over 1 plus GH. My H value is unity here.
Whatever was in box.
It's G over 1 plus GH. When you do a feedback that does this, that's G, and that's H. So you have to do the G over 1 plus GH. In this case, my H is equal to 1. So I've got fractions and within fractions. So let's do S cubed plus 1 over S all over And I'm just going to write these all the way out just because it's there's enough agena here. So this is S plus S cubed plus 1 all over S gives me S cubed plus 1 over S cubed plus S plus 1. Everybody okay with that? When I combine that feedback path? So this term is not that. This is S cubed plus 1 over S cubed plus S plus 1. Okay. Now my G, I'm going to have to cascade these two together. So when I cascade these two together, what I end up with for my G is S cubed plus 1 all over S cubed plus S plus 1. And then I just multiply that by S because that's in the denominator term. That's my G term. My H is here. So this is a feedback. So I have G all over, up a little bit, 1 plus GH. S cubed plus 1 over S to the 4th plus S squared plus S. And then my G term, my H term is here in the numerator, right? So I actually can cancel out that and go back to just making that a 1. So now when I combine those, well, actually, let's not do that because it's going to be too messy. So let's just do it this way. So now when I invert and multiply and combine, I have S cubed plus 1 all over S to the 4th plus S squared plus S to the 4th plus S. So I move those up over there and then I invert and multiply. And that's my final transfer function here. So you can simplify it down right a little bit. I guess we should clean it up a little bit. S cubed plus 1. I notice that there's an S term in all these, so I can factor out an S, and I have 2S cubed plus S plus 2 would be my final answer. That's by doing it, you know, all the steps. And this is what I really, 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 really want to have, because it's the denominator of my system transfer function. So this is what I'm going to monkey with to go ahead and build my system or design my system. All right, questions on that? We can walk through this and we end up with the same thing. If you multiplied all those terms out, you would end up with, because you can see I can factor out an S, right? But you could get the same result. Okay. All right, last couple of slides. We'll move this over here. We have 2 standard forms, and they're going to simplify future analysis is really why we're doing them. And there's one that's called unity feedback, which means H is equal to 1. And one that there's non-unity feedback, which H is not going to be equal to 1. It's going to be a question mark. It's unknown. So that means we have to have a block for our non-unity feedback, H. And for the unity feedback case, H is going to be equal to 1. Okay. This G is our feed forward. H is our feedback. And so what we'll be talking about, particularly when we look at things called steady state errors, we're looking at unity gain in many cases. So we're looking to compare the output directly to the input to calculate what the error is. And the last thing we'll do is when we talk about open loop versus closed loop gain, if we have our closed loop gain for negative feedback, we've done this probably 50 times already, right? We have G over 1 plus GH. We're pretty confident of that. That's the closed loop gain. If we open the loop here, which means that arrow that goes back into our summing junction is actually not connected all the way. So if we wanted to find what that point is what the gain would be for a variable that is over here. Now that doesn't really exist because it does go back to the summing junction, but it goes to that point. We can see to get to this point, our input R gets multiplied by G and then gets multiplied by H. So if we want to do what's called an open loop transfer function for this point here, I don't know, let's call it 325, EET325. So if we wanted a gain, we see that 325 is going to be equal to our input, R, times G and H. So our transfer function, remember transfer is the output over the input. Output's 325, input's 3, is R, is equal to G times H. That is the open loop gain. Okay? Not the closed loop gain, it's the open loop gain. And the way that you find the open loop gain is you just multiply G times H, right? And we're going to see again, when we start doing steady state errors, when we do that type of stuff, it makes things really, really super duper helpful for us. All right. Whoops. And then the last thing in this slide is the characteristic equation. And again, why do we call it the characteristic equation? Because we have a numerator and a denominator. And if you remember this denominator, the roots of that denominator are when we went to the Laplace table and we got the results we were looking for. Oh, this looks like e to the minus alpha t in the time domain, or this looks like sine of omega t, or this looks like e to the minus something times sine of omega t. And that was always determined by what was happening the denominator. So that characterizes the behavior of our system. And since it's the denominator, we're actually going to call that the characteristic equation because it characterizes the behavior of their system. So when we look at systems and we look at second order systems or first order systems, we're actually looking at the characteristic equation to see what the system behavior becomes. All right. And that's why these roots are the poles, finite poles of our system. All right, questions on anything, because that finishes up our topic for block diagrams. Let's take a look at the homework. Let's see. Is this homework number 5 or number 4? I think it's number 5. Number 6. So yeah, number 5 is. Let me see if it's number 6.
It shouldn't be.
Number 6. Did I not post number 6 yet, or did I?
No.
What's that? I'll take a look and see, because I might have had it kick on at a certain time or something like that. I don't know. But either way, I'll make it available after class. But this is homework 6, which you can see. And unless I'm told, unless you're told otherwise, I don't know why this didn't post. That's going to be plus minus. So this one you can see you've got a network in cascade, and then you got a simple feedback path. Then you have another one in cascade. Pretty quick and dirty one. Over here, you've got to do a little bit of work, right? Because you have a summing junction and a pickoff point that are next to each other. So you might need to do a little bit of work moving one or the other. You can move the pickoff point or you can move the summing junction. It's your call, right? You have the table to work from that. And then over here, I'm saying, all right, let's modify our system. And I don't know why the summing junction didn't plot on this one. Now we got to do a really simple block diagram, but I'm actually asking you to plot the response for a unit step input. How would you plot the response of a unit step input?
Would you use MATLAB? to possibly put in your transfer function that you get from your block diagram.
Say more.
So you're giving us a system right here, and it seems in Laplace form, so it's not a terribly complicated system. You're just going to combine those last 2 points. Once you have your transfer function, you can then place that into MATLAB to receive data points, and then plot that using Excel like we did in lab.
Well, I think what you're saying, Brandon, is you can find the transfer function, right?
Mm-hmm.
Is you're going to get C over R. You multiply that by a unit step. Then you have to do partial fraction expansion. And then you plot in Excel, right?
Mm-hmm.
Is that what you're suggesting?
Yes.
Yep, that's one way to do it. Any other ways? One over S is not a constant though, right? It's a unit step, so it, say that again? There is a step, but how would you model that in MATLAB? Remember LTI viewer? We did that last class, the beginning of last class, where you can do a step input. So all you have to do is give it a transfer function. So you find the transfer function over here. You stuff that into LTI viewer, and then you can get the plot that way. I have 3 options. What's the third one? You've been doing it in lab, right?
Mm.
Any one of those 3 will work. The first one is the hardest, most amount of work because you got to do partial fraction expansion and take it back to the time domain and plot it. This is what we're trying to avoid as much as possible in this class, right? If we can, but you can do it. That's just more the brute force method. The LTI viewer in MATLAB, you still need to find a transfer function, but it'll give you a step out. It'll give you a plot based on a step input. And lastly, in Simulink, you can put it in exactly as the block diagram shows and get a plot that way. So number 3 is the easiest. I just don't know if I would suggest that you would do it that way for the homework, only because you still need to be able to find transfer functions. So my suggestion would be try to do number 2 and then check it with number 3. Easy enough to do, right? You just build a Simulink model. It takes you 5 minutes to build it, and then you can do a scope and plot the output. In Simulink, in LTI viewer, you got to do the transfer function. So you got to do a little bit of math, not a ton of math, and you can go ahead and do that. If you really wanted to get, I'll give you extra points. If you want to do all 3 and actually do Excel, the time domain one, and do it in Excel, then that would be another way to do it. But then you can check all 3 if they're the same. But you have options to do that. And then I got a whole bunch of suggested problems. So Aaron, you're welcome. I even included some percent overshoot stuff to make it a little bit. So not too many, but we have a few. All right. Questions on how to do the homework? Helpful to get a little bit of a introduction, because that'll probably be due the Tuesday you get back from break. Okay, let's jump in for a little bit on doing some Ruth Hurwitz. So we'll do a few minutes here today. So on Thursday, maybe I'll cut you out a little early because it's getting close to break and people are almost already on break. Is that fair to say? So let's do a little bit of stuff here so that way we can finish up Ruth Hurwitz on Thursday, and then we can go ahead and, we don't have to have a full regular class. So stability of a system. What does it answer? By both stability. Will bounded or reasonable inputs lead to unbounded outputs? Or will they be bounded? So we have this zero state response and this zero input response, right? So the zero state response is because you have a forced response, you're providing a power supply. The zero impulse response is because you have initial conditions. You have some stored charge in there. Again, we're going to focus on bibostability. And a bibostable system really just focuses on the zero source response, okay? Not the input response. Because that's just, you have your initial conditions. There's not much you can do from that. So here's our system, and don't get worried with all the math. We'll do some math to kind of present the Ruth Hurwitz approach. But this is written sort of generically. Does anybody know what this symbol is? You may not have seen that in math classes yet. Anybody seen that symbol? It's okay if you haven't, it's perfectly fine. It's not the most common, but it is a math symbol that's regularly used. You've seen its sister or brother all the time. What's that? Sigma, which is the sum. What do you think that is? It's the product. That's all that means. So this is a cheesy math way of saying, I'm going to take and multiply all those terms together, S plus Z1, S plus Z2, S plus Z3, on and on and on, all the real zeros of my system. And in the denominator, I'm going to multiply all the poles of the system. That's what the poles are. But I've tweaked it a little bit because I don't want to worry about complex roots and trying to combine those and make those. I'm just going to go ahead and put those as S plus alpha squared plus omega squared, right? Going back to the simple basic way to do complex roots. And we know when we take that back into the time domain, we're going to have perhaps a constant, right? If there's a pole at S equals 0. Pole at S equals 0. And then we start having our decaying exponentials here for both real terms, and then if we have any complex terms. So that's what our system is going to look like. If all the poles are in the left-hand half plane, that's what this said, right? Negative real parts is the same way of saying in the left-hand half pole plane, then the system is going to be a stable system. So that is bibostability, right? The left-hand half plane. It does not include the J omega axis. Why does it not include the J omega axis? Because this is marginally stable. And the reason why it is marginally stable is because you can't guarantee bibostability unless you know what the input looks like, right? So if you have an integrator, a system that acts as a pure integrator, and you hit it with a DC, over time, that's going to blow to infinity. If you have complex roots on the J omega axis and you excite it at that natural frequency, then eventually that system is going to have a sine wave that blows up. Remember the example we talked about, the Tacoma-Narrows Bridge. So we do not include the J omega axis because it doesn't guarantee bibostability. So is this system bibostable? Well, let's go ahead and take a look at the characteristic equation. And let's do the quadratic equation. Or you can use your roots stuff in your calculator. But when we do that, actually, this one's easy enough, right? You could probably just look at it and figure out it's S plus 1 times S plus 2. Now, are both of those roots in the left-hand half plane? They are both negative numbers. So we plot them on the S plane. They're all in the left-hand root, left half plane. So the system is bibostable. Here's a unit step response. We go ahead and take it back to the time domain. And we can see that we have a constant plus 2 decaying exponentials. None of those will blow to infinity. So we're content there. How about this one? Is this one bibostable? Can't tell. And this would be hard to come up with the roots of this one. So we would use a calculator to do that. So here's our characteristic equation. and we have 3 roots. The other thing too, if you have an S cubed over here, or an S to the 4th, the highest order S term in the denominator tells you how many roots you have. So you know by the fact that it's S cubed, you have 3 roots. Now I have S plus 1, S minus 3, S plus 4. We set those equal to 0, and we end up with 3 poles. Negative, negative, but positive. So if I plot this, I plot a pole way over here in the right half plane. Because I have a pole in the right half plane, and not all my poles are in the left-hand half plane, this is not a stable system. It is not bistable. So here's my step response. I come up with this when I do partial fraction expansion, and e to the plus 3t. What happens as time marches on? E to the plus 3t gets bigger and bigger and bigger. The other two, e to the minus t, gets smaller and smaller and smaller. If you don't like writing it this way, that's the same thing, right? And as t increases, the exponent e to the 1, e to the 2, e to the 3 gets to be a bigger and bigger number, but it's in the denominator. So a bigger and bigger number in the denominator results in a smaller and smaller number when it divides up. But this one, the B2 term, does not divide out. That multiplies. So that just gets to be bigger and bigger and bigger. So not a bistable system. How about this one? Can you tell if it's bistable? Well, there's no S term here, right? There's no S to the 1 term there. So if I was to do the quadratic equation, negative b plus or minus b squared minus 4ac all over 2a, that was a 0, right? I have a square root of minus 4ac, which means it's always going to be complex, isn't it? There's no real part here. This is 0. This is always complex, which means that my poles are on the j omega axis. There's no real part. There's only imaginary parts. So this is not bistable because I have 2 poles and they live on the j omega axis. And this is a marginally stable system, right? Not a unstable system. It's marginally stable because over here, when I do my partial fraction expansion and I hit it with a unit step, it doesn't blow to infinity. What I end up getting is something that looks like this, right? It doesn't blow up. It just stays rotating. So this is a stable system because I hit it with a unit step. But if I was to hit it with a sine wave at the same radian frequency, or the natural frequency, what do I end up getting in the time domain? A t out front here. And as time marches on, that K2 term becomes larger and larger and larger until the system blows to instability. So that's why it's a marginally stable system. All right, so this is difficult, isn't it? Isn't that hard to do? Solving for the roots for a polynomial, anything 3rd order and higher, is not easy to do. Maybe with our calculators, it's not too bad. But what we're going to do is try to break it down and see if we can come up with some math to make it work. So let's take a 3rd order polynomial with a bunch of coefficients, a2, a1, a0, and we're going to somehow calculate what the roots are. I'm going to just write it generically, s minus p1 times s minus p2 times s minus p3. Now we're going to multiply all those terms back together, and you'll see why in a second. So you can see all 3 of those multiply the s squared, and then these are in pairs, p1, p2, p1, p3, p2, p3. And then lastly, all 3 are multiplied by together. So essentially what you'd have to do is you have to FOIL it a couple times and then you would get your results. So let's look at our pattern. So our s to the n minus coefficient is going to be equal to the sum of the poles, take the negative of it. Why? Because the negative is over here. Then the an minus 2 term is going to be the sum of the poles multiplied together, but that's plus. And then we're going to alternate plus, minus, plus, minus, plus, minus the whole way down. So we're going to end up with all the way to the A0 that just multiplied. That's, again, this product signal that we see right here. So we can determine if the system has any roots in the right-hand half plane without actually having to solve for this. Why is that? Because if we want, let's just do S plus P1 and P2. We know the roots, negative P1 and negative P2, correct? Everybody agree? If it's in the left-hand half plane, we know that P1 and P2 have to be negative numbers. What happens over here? Negative P1 minus P2 is the sum of those, right? That's a negative up front. Negative P1 minus P2 is a negative number, but doesn't that become P1 plus P2? Let's take a look over here. P1 times P2, these are both negative numbers, right? Equals P1, P2, doesn't it? The negatives cancel out. Positive number, positive number. Hey, what do you know? This results in a positive number. This results in a positive number. So when you're looking at this expression over here, when I look at A2, A1, A0, and when I run them as these pairs, like these pole pairs, or the poles, I should say, you should always, always, always have positive numbers. So if any of these numbers here are negative, it's an unstable system. Any of them are negative. That's my first step. That's called a necessary but insufficient condition. Because if I have s cubed plus s squared plus 2s plus 1, that could potentially still have a pole in the left-hand half plane. But I know for a fact that that negative sign over there means I don't even have to do this Routh-Hurwitz approach. Okay? I don't have to touch it. I don't have to even look at Routh-Hurwitz because I know there's at least one pole in the left and the right-hand half plane. This is an unstable system. So if you ever come across a system that has a negative, they're all positive, but one's negative, it's an unstable system. How about this one? Oops. Is that an unstable system? This is a trick question. Because can't I say this? And remember, I'm looking for the roots of this system, right? That means I set that equal to 0. What happens to the -1? I divide both signs by -1, which means that term goes away. So if they're all negative, you actually could have a stable system. So any sign change, right, means it's a negative number. What about this one? The s to the 1 term is multiplied, you're multiplying that by 0. So if any of the term vanishes, meaning you don't have an s to the 1 term or an s to the 2 term or whatever, then it's got to be an unstable system. So these two rules, missing s term or a negative, a sign change. Oops, I said sig, not sign. If you look for either of these two, you don't have to do any more work. Unless the question is, how many poles are in the right-hand half plane? That's the thing about the Ruth-Hurwitz approach. That'll do it. All right, so let's do the Ruth-Hurwitz approach. We're going to build an array, and it's based on these coefficients. We have a, n. Notice we just multiply the s term times whatever coefficient we want. We have a n, a to the n minus 1, all the way down to a0, which multiplies s to the 0, which is the same thing as 1. Now, we're going to go ahead and start building our rows. The highest order row in our Ruth array is going to correspond to the highest order S term. And so now we start grabbing coefficients. Highest row, we grab that coefficient. Then we skip. We don't grab the n minus 1, we grab the n minus 2 and put that in there. Then we skip a term and do n minus 4. And then all the way until we get down to we have no more coefficients. Now we subtract 1 from our highest order S term, and now we have a to the n minus 1, a to the n minus 3, a to the n minus 5. So we start at the next, next available one, and then we alternate. These first two rows are specified just based on coming up with those results. You just grab the coefficients and you go from there. All the other ones I have to calculate. So here's how I calculate the next set of rows. B1, I'm going to take the negative of whatever is in my AN, let me back up. So if I want to solve for B1, I'm going to take the determinant of that, multiply it by the coefficient that is directly above, and take the negative of it. Anybody know what I mean by taking the determinant of something? So an minus 2, an minus 1, an minus 3. If I take the determinant of that, it's an times an minus 3 minus an minus 1. Oops, parentheses are on the wrong spot. Times an minus 2. That's just the determinant. It's a linear algebra thing. I know a lot of you haven't had linear algebra, but it's basically, that's what that means. So anytime you see this determinant expression, you just go ahead and use that. So to solve for B1, negative 1 over an minus 1 times the determinant of there. Now I'm going to go ahead and show you how to get B2. Let's change the color. To get B2, I'm going to use my determinant approach, but I'm still going to use the very first row. So 1 up above, very first row. But now I'm going to go to the immediate right and 1 above whatever coefficient I'm solving for. So I'm solving for B2. So my determinant is based on an minus 1, and an minus 4, and an minus 5. That's what I've got over here. Okay. B3, if I did B3, let's pick purple. Always using the first row, and then 1 to the right of the coefficient that I'm doing. So if I move this over here, that would be my B3 expression. Once I'm done, right, because if I end up with a bunch of zeros over here, my determinant is going to be 0 times 0, so it's not going to matter anything. Now I'm going to go to my C1 coefficient. So all I need to do to C1 is I move down. Let's pick this color. My C1 now, I'm going to use these two for my first row or column, and these two for my second column. So notice the B1, I grab from right above, and then I take the determinant of an minus 1 and B1, and AN minus 3 times B2. To get C2, hopefully this is legible on the screen. That's C2. I'm going to use these two and these two. And I just keep rinse and repeating until I get to my S to the 0 row, and I should have only one term. The approach for Ruth Hurwitz is the number of sign changes here. Let me change back to a more legible color. The number of sign changes in this first column tells you the number of poles in the right-hand half plane. Okay? That's the Ruth's approach. All right? That's number of sign changes in the first column tells you the value. So let's take a look at an example, and we'll do this one example, and then I'll let you all go. You can finish it up after. So we have a transfer function, a system transfer function is shown. Here's my characteristic equation right here. Now I can see that this is 1, 1, 2, and 8. So I'm going to go ahead and start building my Ruth array. I've got S cubed, S squared, S to the 1, S to the 0. So I immediately just identify the rows that I've got to solve for based on that. Now I've got to solve for, I got to put my coefficients. So to build my A3 row, my S3 row, I grab A3, then I skip and I go to A1. I go to the next row down, I grab A2 and A0. All the other coefficients need to be calculated. So I'm going to calculate B1. So B1, and I'll use my red, is going to be here and here, my determinant. And then I multiply whatever is right above in the row in the first column. So B1 is going to be equal to -1, A2, A3, A1, A2, A0. Plugging in actual numbers, A3 becomes 1, A1 becomes 2, A2 becomes 1, and A0 becomes 8. Those are the actual numbers for this specific one. So I plug in my actual numbers here, -1. I don't know why the number didn't work out here for B1. -1, so the determinant over here, and I'll spell that out. -1 over 1 is -1 times 1 times 8, which is 8, minus 2, which is equal to -6. Okay. This one's pretty easy, right? Because I got a row, I got a column of zeros. So that ends up being 0. There's -6, 0, 0. How many sign changes in the first row? The first column. Everybody agree there's one sign change? Anybody agree? I don't agree. Plus, no sign change there. Oh, minus, one sign change. Plus, sign change there. Don't I have 2 sign changes? I'm not counting negatives, I'm counting changes in sign. So from plus to minus is 1, and from minus to plus is 2. So I should have 2 poles in the right-hand half plane. This is an unstable system. Check it out in MATLAB. Does MATLAB agree or disagree? Do you have 2 sign changes? Or do you have 2 poles in the right-hand half plane? Sure. Aren't these positive numbers? And if I was to do a pole 0 map, I don't think I did the pole 0 map. Oh, I did do the pole 0 map. Here is the j omega axis. What do you know? I have 2 poles in the right-hand half plane. Okay. Now, I'm not going to do this example, but I will ask a question. The question is, it's a lot of work, even to do the Ruth Hurwitz stuff, right? So you might be asking yourself, Paul, you did all this work back here to tell me there were 2 poles in the right-hand half plane. Couldn't I have just done exactly this in MATLAB and told you that? way less time. Everybody agree with that? What if I changed it so that this is not 2, but it's some variable k? Now I wanted you to pick a value of k that results in a stable system. Can you put that in MATLAB? No. You cannot. So the real reason why we do the Routh-Hurwitz is it's a design capability. What we're going to start to see is you're going to get variables in your characteristic equation because you can change something about the system. And because you have those variables available to you, you can get different design criteria, but you have to limit that design criteria to make sure your system is stable. So the real reason why we spend so much time doing Routh-Hurwitz is because we can't use MATLAB, we can't use a calculator to do that, unless you want to just do trial and error and get results. Okay, we're engineers, right? We're going to be engineers. So the purpose of being an engineer is being able to design a system. So taking advantage of the skills that you all have to be able to design a system. Okay. Questions on this? Because we'll pick it up here. If anybody wants to practice on their own, that's a good way to go ahead and do that. Any questions in TV land? Thanks for those of you who kept your cameras on. It's likely to see your smiling faces. Okay. Well, if there's nothing else, you all have a great day. And I will see you guys around. We do have a lab tomorrow, but it's going to be like a study session. So Mark and I talked about it. Should be a little bit of a design thing. So hopefully it'll be pretty interesting. But, all right. Take care, everyone.
Thank you, Paul.
Thank you.